that when we're talking to each other at these high and complicated levels, and we think we're speaking very well, and we're communicating, but what we're really doing is having some kind of big translation scheme going on for translating what this fellow says into our images, which are very different. I found that out because at the very lowest level, I won't go into the details, but I got interested in, well, I was doing some experiments, and I was trying to figure out something about our time sense. And so what I would do is I would count, trying to count to a minute. Actually, say I'd count to 48, and it would be 1 minute. So I'd calibrate myself, and I would count a minute and 48. I think I was counting seconds, but it's close enough. And then it turns out if you repeat that, you can do very accurately. When you get to 48 or 47 or 49, not far off, you're very close to a minute. And I would try to find out what affected that time sense and whether I could do anything at the same time as I was counting. And I found that I could do many things. I could, there were some things that not. For example, I had great difficulty. I was in the university, and I had to get my laundry ready. And I was putting the socks out, and I had to make a list how many socks, and it was something like 6 or 8 socks, and I couldn't count them because the counting machine was being used, and I couldn't count them until I found out I could put them in a pattern and recognize the number. And so I learned a way after practicing by which I could go down the lines of type in newspapers and see them in groups 3, 3, 3, 1, that's a group of 10, 3, 3, 3, 1, without saying the numbers, just seeing the groupings. I could therefore count the lines of type I practiced in the newspaper at the same time I was counting internally the seconds. And so I could do this fantastic trick of saying, 48, that's a 1 minute, and there are 67 lines of type, you see. It was quite wonderful. And I discovered many things I could read while I was, excuse me, yes, I could read perfectly all right while I was counting and get an idea of what it was about. But I couldn't speak, I couldn't say anything. Because of course I was sort of, when I count, I sort of spoke to myself inside. I would say 1, 2, 3, sort of in the head. Well, I went down to the breakfast, and there was John Tukey was a mathematician down at Princeton at the same time, and we had many discussions, and I was telling him about these experiments and what I could do. And he says, that's absurd, he says. He says, I don't see why you would have any difficulty talking whatsoever, and I can't possibly believe that you could read. So I couldn't believe all this, but we calibrated him. It was 52 for him to get to 60 seconds. It repels you is very good for understanding the stiffness of material. That it's a wave which does this and that is very good for some other phenomenon. All right? So when you're working with certain particular aspects of the behavior of atoms, for instance, when I was talking about temperature and so forth, that they're just little balls is good enough, and it gives a very nice picture of temperature. But if you ask more specific questions and you get down to questions like, how is it that when you cool helium down, even to absolute zero where there's not supposed to be any motion, it's a perfect fluid that hasn't any viscosity, has no resistance, flows perfectly, and isn't freezing? Well, if you want to get a picture of atoms that has all of that in it, I can't do it, you see. But I can explain why the helium behaves as it does by taking my equations and showing that consequences of them is that the helium will behave as it is observed to behave. So we know we have the theory right, but we haven't got the pictures that will go with the theory. And is that because we're limited and haven't caught on to the right pictures? Or is that because there aren't any right pictures for people who have to make pictures out of things that are familiar to them? Well, let's suppose it's the last one, that there's no right pictures in terms of things that are familiar to them. Is it possible then to develop a familiarity with those things that are not familiar on hand by study, by learning about the properties of atoms and quantum mechanics, by practicing with the equations until it becomes a kind of second nature, just like it's second nature to know that if two balls came toward each other, they'd smash into bits. You don't say the two balls, when they come toward each other, turn blue. You know what they do. So the question is whether you could get to know what things do better than we do today. As the generations develop, Will they invent ways of teaching so that the new people will learn tricky ways of looking at things and be so trained, so well trained, that they won't have our troubles with the atom picturing? There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. I think that's a deep prejudice. It's a prejudice from being so used to large-scale behavior. And they're always seeking to waiting for the day that we discover that underneath the quantum mechanics, there's some mundane, ordinary balls hitting or particles moving and so on. I think they're going to be defeated. I think nature's imagination is so much greater than man's, she's never going to let us relax.